The aim of this presentation is to investigate the failure induced by microscopic stability phenomena by means of the application of multiscale techniques in fiber-reinforced composite materials. Composite materials are used in many engineering applications by virtue of their better performance compared to conventional materials, for instance, their capability to undergo large deformations. When such materials are subjected to high loading levels, may exhibit instability phenomena at the macrostructural scale, which are usually considered as a precursor of failure due to their strong interaction with the other microscopic dynamic processes. These instability phenomena may be geometrical or material dominated, and some typical examples of such instabilities are reported in this slide. In addition, such materials can be subjected to microscopic damage processes. These processes, often involving self-contact phenomena between crack faces, interact with microscopic instability phenomena and may induce a premature failure of heterogeneous of solids. In the specific case of unidirectional fiber-reinforced composite materials, the interaction between buckling stabilities and fracture may lead to a strong decrease in the compressive strength of the composite material, since buckling causes a large increase in energy release rate at the tips of the pre-existing cracks, favoring the crack propagation or the interface debonding. The exact determination of their nonlinear response is still a challenging task, and accurate results could be obtained by using full-scale direct numerical simulations, but the associated huge computational effort makes them unpractical for real-life application. This situation motivates the necessity to introduce efficient multiscale approaches to predict the onset of failure in these materials, investigating their macroscopic behavior. The composite material is assumed to have a periodic microstructure described by a suitable representative element. This domain may contain cracks whose opposite surfaces may undergo frictionless self-contact. Each constituent is characterized by an incrementally linear constitutive law relating the rate of the deformation gradient tensor to the rate of the first Piola curve stress in terms of the tangent moduli tensor. The RV is subject to boundary condition depending on the macroscopic deformation gradient, and the solution of the corresponding nonlinear equilibrium problem gives the macroscopic first Piola curve stress. The macro and the macro scales are coupled to each other by means of the classical relation that define the micro variables in terms of the deformation interaction on the boundaries. By splitting the microscopic deformation field in a linear part and in a fluctuation one, it follows that an integral constraint must be imposed on the fluctuation field, and according to the periodic nature of the composite microstructure, this constraint can be satisfied by enforcing periodic fluctuation on the boundary of the RV, and it leads to periodic deformation and antiperiodic traction on the RV boundary. Here, the rate equations governing the rate equilibrium solution of the microstructure are reported. They can be derived by means of an asymptotic expansion at a generic time t and can be defined in terms of the fluctuation rate solution. Specifically, the first-order asymptotic expansion of the non-penetration in the mechanical contact conditions leads to the following rate constraints at a generic contact point pair. Moreover, the second-order asymptotic expansion of the unilateral mechanical contact condition gives its corresponding rate version. In addition to the classical rate equilibrium condition for the microstructure, we obtain the traction rate continuity condition and the tangential traction rate condition at the crack contact interface. In view of the subsequent stability and bifurcation analysis, it's convenient to characterize the rate response of the microstructure in a variational form. To this end, the set of kinematically admissible fluctuation rates is here introduced. Considering the rate equilibrium condition at the frictionless crack contact interface in conjunction with the mechanical contact rate condition, the work done by the nominal contact reaction through the virtual displacement consists in two contributions: the tangential component of the nominal contact reaction rate A and the crack surface relative deformation B. Then, the uniqueness of the rate response is ensured when the following positivity condition is satisfied for the functional R, whereas an incremental stability criterion can be obtained by considering a small perturbation of the current equilibrium position giving the following stability condition. In previous outdoor works has been demonstrated that in presence of nonlinear effects induced by the contact reaction, stability and bifurcation condition are not coincident, and that the stability condition is not critical. For this reason, special classes of incremental contact mechanisms have been identified. One is the case of effective contact, for which stability implies the uniqueness of the solution, and the other is the case of conservative incremental contact loads, for which the loss of stability implies bifurcation of homogeneous loading. In more general case, upper and lower bound of the critical loads can be obtained by means of incremental linear comparison problem. Regarding the computational implementation, a one-way coupled finite element model is adopted to compute in a sequential way the principal solution of the unit cell and the associated eigenvalue problem, providing the stability load factor for a given macrostrain path. The incremental boundary value problem for the microscopic stability analysis is obtained by adding this eigenvalue term to the weak formulation. The corresponding critical load level can be found as the load parameter associated with the lowest zero eigenvalue. This numerical procedure has been also used in recent works in which complete microscopic stability domains were obtained by means of several stability analyses computed for different radial loading paths in the principal macrostrain space. The animation shows a typical load parameter displacement response with the displacement measured as illustrated in the picture, in addition to the principal solution path. The response of the representative volume element containing a geometric imperfection triggering bifurcation by continuation of the principal path is plotted for the comparison. Here, the introduction to semiconcurrent multiscale model is reported with the aim to develop a multiscale method able to analyze the macroscopic compressive failure behavior of defected periodic fiber-reinforced composites subjected to large deformation by implementing also in the computational procedure the previously developed theoretical formulation. Specifically, a Fe-square-like multiscale model was adopted in which the macroscopic constitutive response of the composite structure was extracted by solving a microscopic boundary value problem linked at the macroelement of the homogenized domain. The information are transferred on the fly during the simulation from the lower to higher scales and vice versa, establishing a two-way weak coupling. In addition, in order to avoid the evaluation of the critical load at each load step through an eigenvalue problem, the two-dimensional stability and uniqueness domains presented in some other works has been also used. The first multiscale application considers a composite material reinforced with continuous fibers arranged according to a unidirectional pattern subjected to homogeneous macroscopic deformation. In the semiconcurrent multiscale analysis, the microscopic periodic unit cells are connected to the homogenized continuum in order to obtain the macroscopic response along the principal path. In the meantime, the macro deformation state of each microscopic cell has been monitored by means of the two-dimensional stability and uniqueness domain. A convergence analysis to the RV sides has been incorporated in numerical procedure in order to verify the coincidence of the mode shape and the critical load level between a single cell and a cell assembly of increasing dimensions, and the obtained critical load factor is equal to 0.1139. Then the obtained results have been compared with the stability analysis performed on a direct numerical model based on the explicit discretization of the heterogeneities of the composite microstructure, and the obtained critical load parameter value is equal to 0.1172. The results are reasonably accurate when compared with the critical load predictions of the direct numerical analysis. The relative percentage error of the critical load level, about 3%, is due to the boundary layer effects induced by the external constraints. The second application concerns a cantilever composite beam reinforced with continuous fibers subjected to a bending stress induced by a concentrated vertical force applied at the free end of the beam. The numerical analysis of the homogenized model was conducted assuming quasi-static displacement-controlled loading condition. In the animation, the von Mises stress map of the macroscopic multiscale model is reported together with their linked microscopic representative elements. In addition, here is shown the zoom on the critical cell and the curve representing the vertical reaction versus the macro displacement. It's worth noting that such curves shows a load jump in correspondence with the critical load factor that was measured by a means of graphic extrapolation, and it resulted about of 30 micrometers. However, in order to evaluate the accuracy of the multiscale model prediction, the lower bound of the primary stability and bifurcation load was assessed through a linear comparison problem. The evaluated lower bound value is equal to 26.43 micrometers. A comparison between results of multiscale and direct numerical simulation are discussed here. The critical load factor is obtained by a graphic extrapolation, and also a critical load lower bound has been evaluated. As expected, in both multiscale and direct analysis, the obtained lower bound of the primary stability and bifurcation load is lower than the exact critical load factor. The relative percentage error between the two different simulations are 1.5% and 0.3% respectively. Thus, such numerical results demonstrated the capability and the effectiveness of the adopted multiscale model to predict the critical loads for primary stability and bifurcation. In conclusion, by modeling unilateral self-conduct between crack surfaces by means of a full finite deformation approach, the adopted formulation is able to analytically derive the non-standard loading contribution in the work of the contact reaction rate. In addition, the present formulation could be adopted in the context of multiscale approaches for predicting the failure behavior of locally periodic defected composite solids subjected to large deformation. The numerical analysis carried out for microscopic loading involving both homogeneous and inhomogeneous deformations in the homogenized solid showed that a two-scale homogenization approach is able to give accurate prediction of the critical load levels associated to macroscopic stability or bifurcation, as confirmed by means of comparison with a direct analysis with an explicit meshing of all of heterogeneities. Whereas future developments concern the investigation of the failure behavior of fiber-reinforced composite materials in presence of microfractures by means of an adaptive concurrent multiscale model in which the onset of failure domains are used as criterion to identify the critical regions, with the explicit aim to enrich these zones with detailed microstructures, while in the non-critical zones, a nonlinear macroscopic law can be adopted by means of a semiconcurrent or microscopic strain stress database approaches. Thank you for your attention.